In the case of elastic potential energy, here we do the same study. First of all, we have an elastic object. This one is elastic object with K constant. And here we have an object of mass M. And the plane is a frictionless. We don't have mu. Initially, let's say here, okay, this one is a position 1, position 2. I want to study the motion between position 1 and position 2. And here we have the equilibrium position where x equals to O. Initially, the object was at this point, at this position. I push the object to the right slowly with FA. Okay. So I push to the right with FA. The displacement will be between the initial point to the final point. Here we have dr, but in this case, dr equals to dx, okay? Dr equals dx. We don't have dy. And dx in the positive direction, here we have dxi. As you see, in general, we have mg and we have n. And we have Fa applied on the object. When you move the object to the right, the spring will resist the motion with Fs. And you know, Fs must be directed toward x equals to 0. In the last videos, we calculated, we said Fs equals to Fa as magnitude. And also the work done by Fs equals to minus the work done by Fa. We calculated omega Fs, which is equal to minus half kx square final. I am studying now between 1 and 2. So at 1 here, initially we don't have velocity initially. So V1 at this point equals to O. And at the end, at the position 2, also we don't have velocity. V2 equals to O. Between 1 and 2, because the slow motion, the velocity equals to a constant value. Okay. Here, the final position is 2, half kx2 square minus half kx1 square. The final position and the initial position. Okay, in this case, x1 equals to O because it was at the origin here. We don't have x1. And you know, the definition of the elastic potential energy, PE elastic, equals to half kx square. So here we have the final potential energy minus the initial potential energy. We can write omega Fs equals to minus potential energy elastic at the position 2 minus potential energy elastic at the position 1. We can say equals to minus delta potential energy elastic between 1 and 2. Okay, from 1 to 2. And as omega Fa equals to minus omega Fs, we can write finally we have omega Fa equals to minus omega Fs. So omega Fa equals to delta potential energy elastic and omega Fs equals to minus delta potential energy elastic. Here we can use these relations directly. Let's take some energy analysis, okay? Now, you know, at the position 1, we have, in this case, we don't have V. Okay, in general, the mechanical energy 1 equals the total kinetic energy at the position 1 plus the total potential energy. Here we have potential energy G plus potential energy elastic. You know, for the case 1, okay, for the case 1. Here we don't have velocity at this point, so we don't have kinetic. Plus, here, let's take the x-axis is here and y-axis is here. So the height of the object between the initial point and the final point, we have the same height, y equals to O. We don't have height. When we don't have height, we don't have a gravitational potential energy. So we don't have mgh. Okay? Because PEG1 equals to mg y1. We don't have y, so we don't have PEG. Plus, at this position, we don't have x equals to 0. So here we can say k over 2 times x square 0 square. So the total mechanical energy here equals to 0. Here we applied omega Fa between the initial point and the final point. So we have some quantity of energy, omega Fa, is consumed here. So omega, before talking, we have omega Fa consumed between the initial position and the final position. It's a positive value. So we add a quantity of energy on the system, okay? So this quantity of energy, omega Fa, is added to the system. Okay, till now, at the position 1, we don't have any kind of energy. So at the position 1, we don't have energy. We can say here the total energy here equals to O. Second, between 1 and 2, we add a quantity of energy equals to omega Fa here. Okay, at the final position, at the position 2, what we have here? we don't have velocity, so energy total equals to O. We don't have kinetic energy. We don't have height, so the potential energy G equals to O, but we have X. We have X at this position. So here we have a elastic potential energy PE2. This is the total energy. So what the conclusion at this point? The conclusion is, here at this point, the total energy equals to O. Between this point and this point, we add omega Fa energy. At the position final, we have E total equals to elastic potential energy. I see here that the energy consumed omega Fa is converted to the potential energy elastic. Okay, it's clear now. So between 1 and 2, the work is, excuse me, between 1 and 2, we added omega Fa. Why we added? Because it's a positive value. Okay, it's a positive value. Look, at the position 2, this energy is converted to a elastic potential energy. We have just a potential energy, so the work is converted to an elastic, let's say, to P E E. Here, don't forget, we don't have interaction between the block and the plane. I think it's all about the elastic potential energy. I can give a simple example here. Let's say initially the object is at this position. We can say here position 1. And the object, so this is the initial position. Here we don't have Fa. We have just Fs applied on the object by the spring. And here we have the equilibrium position. Okay, initially the object, this is an exercise, okay? Exercise. Example. At this position, V equals to O. So as we don't have a V, we don't have kinetic energy also. Okay, we talk about the energy later. We release the object without initial velocity because the object was at rest. When the object moves to the left, we have a displacement between this point, and I want to study between this point and this point. This is the position 1 and the position 2. Let's say here we have a displacement dr, which is equal to as you know, dr equals to dx plus 0 dy. dr is directed to the left, so here we have minus I dx. Okay, we have this displacement. The only force applied on the object is Fs. You know, in general, the work done on Fs or by Fs equals to minus delta elastic potential energy. You have to apply this relation directly. I need to calculate omega Fs. So equals to minus the I am working between position 1 and position 2. So position 1 is the initial position and 2 the final position. Delta potential equal the potential at the position 2 elastic minus potential at the position 1 elastic equals minus at the final position here we have x equals to 0. And you know the potential elastic equals to have x times k times x square minus at the position 1 we have x, okay, from here to here. So we can write half times k x square. We get finally minus times minus we have plus k over 2 x square. This is the value of omega Fa. Now I want to study the total energy at each point. Here at the position 1 we don't have velocity, so the kinetic energy Ke1 equals to O. Here we have velocity because the object moves to the left. You know, when I release the object at this point, the object will accelerate to the left. It arrives to the position x equal to O with a velocity v. And also, this object will continue to the left, after to the right, to the right, to the left, to the center, to the maximum left side, here and here. You will get some oscillation. So in general, at x equals to O, we have the maximum velocity. So we have a kinetic energy 2, which is equal to half mv2 square. We have a kinetic. But at this position, we don't have x. So potential energy elastic equals to O. And here we have potential energy elastic 2 equals to half kx square. So between 1 and 2, what we have? I want to study the energy of the system. It's very important. At 1, we have only elastic at the position 1 here. We have only elastic potential energy. Okay? And at the position 2, we have just a kinetic potential kinetic energy. So what we have here, the energy of the elastic potential energy is converted to the kinetic energy. Okay? you have to understand this point. You have a transformation of energy between elastic potential energy at the position 1 to the kinetic potential energy at the position 2. Okay, so the elastic potential energy at 2 at 1 is converted to a kinetic energy at 2, at the position 2, between this point and this point. Okay, I think it's all about the elastic potential energy. Let me talk about the internal energy. Don't forget, here we don't have an interaction between the object and the plane. In the next video, we talk about the internal energy.